Good morning, everyone. Welcome to sixth recitation in solid waste management course. In this recitation, we will have three different questions, and all of them are related to the combustion systems. And if you are ready, let's start with the first question. In this question, we have a combustor and we burn solid waste, so we produce energy and inert materials as a result of this combustion activity. And the table that shows the average municipal solid waste composition from a combustor is presented in the question. And also, specific weight of residue and waste are given as 1,000 pounds per yard cube and 375 pounds per yard cube, respectively. And by using this information, first we need to find the quantity and the composition of residue that comes from the combustor, and then the reduction of the waste volume. And firstly, let's assume that we have 1,000 pounds of waste, and by multiplying this number with the weight of percentages given in the question, we can calculate the mass of waste for all waste components. And for example, for the food waste, the relative or relevant percentage ratio is given as 15%. So we should just multiply 1,000 pounds with 50%. And actually, this step should be repeated for the other system components. And then to find the inert residue mass, we should multiply the mass values that we have calculated before with the percentage of residue, which is also given in the second column of this table too. And to illustrate, again for the food example, we should multiply 150 pounds by 5%. So we can estimate the inert residue amount due to the food as 7.5 pounds. And again, this procedure is valid for the other system components. And after we estimate all inert residues one by one, we can find the total inert residue mass by adding them together. And actually, this number is equal to 246.33 pounds. And actually, up to now, we found the quantity and the composition of our inert residue. And the next step will be the calculation of the volume reduction of our waste. And to do that, first, we should find the initial or original volume of solid waste by just dividing total mass by the waste density. And so we can estimate the initial volume of solid waste as 2.67 yard cube. And then we should find the final, or let's say residue volume of solid waste with the similar procedure. And we should divide the total mass of residue, which is 246.33 pounds by the 1,000 pounds per yard cube. So basically, we can find the residue volume as 0.246 yard cube. And now we have sufficient information to calculate the volume reduction. To estimate it, we should subtract the final volume or residue volume from the initial solid waste volume, and then we should divide this number by initial solid waste volume and multiplying this number with 100. And finally, we can reach the waste volume reduction value as a result of this combustion process, and it is equal to 90.78%. Actually, this is the end of first question. Do you have any questions about the first one? If you have no question, then let's continue with the second question. In this question, again, combustion process is applied with the air and organic solid waste insertion into combustion chamber. And pentane or C5H12 is specified as the chemical composition of this organic waste. And also the specific weight of air and oxygen percentage inside the air are given as 0.025 pounds per feet cube and 23.15% respectively in the question. And there is also one more information about the unit conversion from ton to pound. And by using this information, we need to estimate the air required for the complete combustion of 1 ton of solid waste. But before jumping to the solution, let's have a look at our chemical reaction. According to this chemical reaction, to combust 1 mole of solid waste, or let's say pentane, 8 mole of oxygen is required. as you can see in this chemical reaction. And if we write the relevant mass values by considering the written molar numbers, we can say that to combust 72 gram of solid waste, 256 gram of oxygen is needed. However, we should find the oxygen amount for the 1 ton of solid waste, like specified in the question. So we should divide the oxygen amount, which is 256 gram, by molar mass of solid waste, which is 72 grams. And be careful at this point. In the question, the desired unit is pound, but we have found the required amount on the basis of ton. And that's why we should apply the unit conversion. And since 1 ton is equal to 2,000 pounds, if we multiply the value that we found before, we can calculate the required oxygen amount as nearly 7,111 pounds per ton of solid waste. And now we can estimate the required air amount by using the relationship between the air and oxygen. And as specified in the question, 23.15% of air composes of oxygen, and therefore, to find the air amount, we should divide the required oxygen amount by this percentage value. And so we can estimate the required air amount as 30,717.5 pounds per ton of solid waste. And the last step will be to find the volume of this air, basically. And to do that, we should divide the required amount of air by specific weight of air, which is 0.075 pound per feet cube. And as a result of this division, we can find the volume of required air as nearly 10,000 feet cube for 1 ton of solid waste. Actually, this is the end of second question. Do we have any question about the second one? Okay. If you don't have any question, let's continue with the last question of today's recitation. In this question, there is a combustion unit that uses refuse-derived fuel to produce energy. And the composition of this fuel is given also. For example, 85% of it forms from organics and 10% of it comes from the water. And the remaining one is inorganics, or let's say inerts. And the inlet ratio of this fuel is specified as 1,000 kilogram per hour also. And then the heat content of this fuel is given as 19,000 kilojoule per kilogram on a moisture-free basis. And the airflow is specified also 10,000 kilogram per hour. And moreover, some ratios about the heat loss, and the ash temperature after the combustion chamber are discussed in the question. And finally, specific heat of ash and air and latent heat of vaporization are also given in the question. And the question asks us what the temperature of the stack gases is. And now actually we have a lot of information that can make the question hard to understand. So drawing a flow chart of the question and write the given parameters onto this figure can help us about the solution of this question. And here you can see the relevant flow chart of question 3. Basically, we have a combustion chamber at the center, and stack is located in the right-hand side of this page. And in the left-hand side, you can see inputs as air and refuse-derived fuel. And composition of this fuel and air and fuel flow rates are also shown in this chart. And by using these inputs, we can combust the fuel and produce heat. However, because of the water vaporization that is found our refuse-derived fuel, and heat transfer process, inert materials inside the chamber, and also wall materials and the conditions will lose some kind of heat. And in the upper part of combustion chamber, you can see these outputs named heat production and the heat losses. And because of these heat losses, the temperature of stacked gases shows a change, and that's why we will calculate the value of these stacked gases in this question. And to do that, firstly, we should estimate the produced heat in the combustion unit and then the heat losses. And the difference between these two components will be used to calculate the total heat emissions from this stack. And to find the generated heat from combustion, first, we should multiply the fuel inflow rate with the organic portion of our refuse-derived fuel, which is equal to 85%. And then we should multiply this number with the heat content of this fuel, which is 19,000 kilojoule per kilogram. And therefore, the heat amount is calculated as 16,150,000 kilojoule per hour. And then we should calculate the heat losses. Firstly, some portion of heat is lost due to the water vaporization, as I said before. And so we should include this portion into our calculations. And to find it, first, we should multiply fuel in net flow with the percentage of water, which is 10, to find the water flow rate. And then we should multiply this number with the latent heat of water. Therefore, the heat loss due to the water vaporization is calculated as 257,500 kilojoule per hour. And the other heat loss because of the radiation effect. And in this question, it is specified that 5% of heat input that has been calculated as 16,150,000 kilojoule per hour before. And therefore, if we multiply this input heat with the loss percentage, we can calculate the heat loss due to the radiation as 807,500 kilojoule per hour. And now we have found the second heat loss components in our system. And now there is one more item that causes the heat loss in combustion unit system. And the heat loss in the ashes in both sensible heat in the ashes as well as the unburned fuel. So first we should calculate the total amount of ash, which is the summation of inert materials inside the fuel and unburned organics that is specified in the question also. And if you multiply the percentage of inert material, which is 5% with the fuel flow rate, we can find the inert materials flow rate. And then remember the question, it is specified that 10% of fuel remains uncombusted in the ash. And at this point, we should consider 10% of combustible portion or organic portion of the fuel. So first, we should multiply fuel flow rate with the 85% to find organic mass flow rate, and then 10%. And therefore, we can find the total amount of ash flow rate. And now we should calculate the heat loss due to the hot ash by multiplying this number with the specific heat of ash, which is equal to 0.837 kilojoule per kilogram times centigrade degree. And the outlet temperature of combustion chamber, which is 800 centigrade degree, is specified in the question. And now we have calculated all the heat losses, and therefore we are ready to estimate total heat emissions in the stack gases. And to do that, we should subtract all heat losses that we have found before from the produced heat in the combustion chamber. With this way, we can calculate the heat emission as 50 million kilojoule per hour. But up to now, we did not include air into our heat calculations because in the question, again, it is assumed that the under and over fire air contributes negligible heat. But in our stack case temperature calculation, we need to include this value since, it is our transfer medium. And therefore, our last step is about the calculation of temperature of stack gases. And as you know, total total airflow, which is 10,000 kilogram per hour, and specific heat of air that is equal to 1 kilojoule per kilogram times centigrade degree are specified in the question. And if we divide our heat emission value by the multiplication of these numbers, we can reach the relevant temperature data as 1,500 centigrade degree. Well, this is the end of third question of the sixth recitation. If you have any question, you can ask me.